This is not so simple linear regression. Up till now, we had a straight line between two variables with an x and a y, and there was no changes in the x and y. It was like fish length and fish weight. That isn't necessarily the case. Simple linear regression just means a straight line and one x and one y. But the x and the y don't have to be as simple as length and weight. They can be transformed as long as we fulfill the assumptions for the regression. There are actually 4 assumptions for simple linear regression, 4 main assumptions. 2 of them are difficult to test, and most people just wish them away and say, yes, they're fulfilled or the regression is robust. But the 2 main ones that we have a problem with is, 1, nonlinear data. And this happens often with growth, with an x and a y, so that we have a relation that's curved. Also, that goes along with this curve, there's a scatter so that it's fan-shaped. We can also have what looks like a linear relation, except it is fan-shaped. It's got a straight line through the center of it, but as you go out in x, y becomes more variable. This is like the height of people. When they are very young, there's not a lot of difference in height. As they get older, the height increases and the difference becomes more obvious. So what we really want to have is an x and a y where we can put parallel lines on the data so that the data is contained. It has no particular flare, it has no particular curve. We can achieve this if we have problem data with a fan or a curve by using a transformation. Both x and y can be transformed to make a linear relation that we can put parallel lines bound on in some way. For example, this is radius and area. And this is purely pi r squared. But if we graph these two, radius versus area, we get a curved relationship. We can put a straight line through it using add trend line, but we miss at the high end and the low end, and then in the middle it's below the line. So we have a perfect relation, but it is not linear. The way to fix this is to use radius squared instead of just radius. So if we square the radius, and graph radius squared versus area, put a new graph in here, the x values now are r squared, and the y values are area. So now we have a perfect straight line between area and radius squared, so that we can transform the x in this case by squaring it and make it into a much better relation. And in particular, we get a perfect relation with area and radius squared. So we can do the same thing with the y variable, and we can use both a transformation on the x and on the y. Anything we do that gives us a straight line relationship, a linear relationship, without any flare in the data is completely statistically legal. It doesn't have to mean anything biologically to be effective. In my open math, we want tree biomass data. Download this file. And there are some results in here already that we really don't need. We can erase this and get rid of the borders, the leftover lines. But here we have tree biomass in pounds by tree diameter. This is measured 4.5 feet above the ground. It's the diameter of the tree at that point. That's in inches, and the height is in feet. For the biomass, you pick up the tree and weigh it after it's cut. This is branches, leaves, bark, wood, anything that's in that tree, and that's the weight of the tree. If we do a plot of the biomass versus diameter, diameter is going to be the x and biomass is the y. Select data, add the series. The x values are diameter and the y values are biomass. And here we get a reasonably good relationship that's got some curve in it, and it's also flared because as the trees get bigger, there is more difference in the weight of the tree. A small tree is a small tree. There's not a lot of difference. When you get to a larger tree, there's possibility for more weight. If we put a straight line through this with add trend line, we get a reasonably straight line. And if we display the R-square, it is 0.88, which is not bad. Fitting the straight line works pretty well, but we still have observations in a flare where they get more spread out as the diameter becomes larger. We can try and fix this with the diameter squared, like we did before, with the radius. So that's diameter squared, and if we make a chart of that, insert bubble chart, click inside, select data, add, and now we want the x values to be the diameter squared and the y values to be biomass. And we get some improvement, particularly in a linear sense, but we still have a flare. Trees, particularly pine trees, are basically cones, so that the volume of a cone is 1/3 the base times the height. If a tree is very much like a cone, we're just measuring the diameter a little bit higher, but we should be able to get the same kind of thing using a radius squared or diameter squared times the height. So we're going to make the x value now diameter squared times height. So move this one to the side, and now this is going to be diameter squared times height. So all we need to do is multiply our diameter squared by the tree height, and now if we use diameter squared times height against tree biomass, select data, add, and now if this is d squared times height, and the biomass, and we get a nearly perfect relationship, straight line with no variance, no changes all the way down the line. So that diameter squared times height gives us volume, and volume times weight per cubic foot gives us biomass, so that this is a duplicate of using a cone of the d square h to get the volume and then get the weight, so that we have both d square and height included in the model, and it predicts height very, very well. We put in a trend line and look at the R square. The R square for this is almost 1.9966, so it couldn't be much higher no matter what we did to it. So that by transforming the x variable, we have gone from a flare and a curve to a very, very straight line. This transformation is justified because it's biologically what a cone looks like. It's what a tree looks like, particularly a pine. But we aren't restricted to what makes sense biologically or even mathematically. Anything that makes the transformation we need is fair game. Back in My Open Math, we have tree and fish line transforms. This file contains both tree and fish data, and here we're on the fish page, and if we graph the length times the weight, we should get a pretty good relationship because the two are related, but we have a fan shape, so that larger fish or longer fish can have more variable weight than small fish. To fix this, we need to get rid of the fan so that we can say we have some kind of relation. The usual fix for this is to use the natural log or the base 10 log of the y variable. So our y variable, instead of weight, becomes log of weight. If we calculate this, equals ln, this is the natural log of weight, the numbers that went from 30 or so to 101 now are all in the 4.2, 4.3, 3.5 range, so that all we have done with this is squash the y variable axis. And if we graph length versus the log of weight, select data, add, the x values now are still length, but the y values, instead of being weight directly, are now the natural log of weight. And if we look at these two things, the log of weight simply squeezes the y values and makes them into much more of a straight line. If we put a trend line through it and display the r squared value on the chart, we get an r square of 0.466, 0.47. If we do the same trend line in the original data and display the r square, we have a smaller r square, but the difference is not so much in the r square as it is in the fulfillment of the assumptions for the simple linear regression. This much more fits the assumptions of linearity and no flare, rather than the original data. Part of the problem with the original data is that the line has to go through the average x and average y, and the line can move up and down in the higher values of length, but down in the lower values it's fixed, so that we can't do like we did before with the residuals where the line is free to move in both directions. So that this makes the assumptions more reasonable, and this would be what we would use to predict the weight. The problem with this is now, if we use the equation to predict log of weight, we get log of weight. We don't get weight directly. So that to get weight from the slope and intercept, I would have to predict the weight and then take e to that power to get the weight. So everything to do with the regression concerns the log of weight and not weight directly. So that's a drawback for the predictions. We aren't minimizing the sum of squares of weight. We are minimizing the sums of squares of error of the log of weight. Also, there is no biological justification for this. The log transform simply squashes the y-axis, and we remove the flare simply by squeezing on that y-axis and flattening it out. Another example of a transformation that has no biological justification is the tree age and height. And if we graph height by age, height is y, age is x, make a scatter plot, you can see that it has a definite curve in it, and it has a little bit of a flare, not much, but if we put a straight line through it, it's going to miss at the lower values on the high side and the higher values on the low side, and miss in the middle as well. So that we need some kind of transformation for this. And one thing that we can do, like we did before, to squash the y values, is to use the log of height. And again, this is the natural log. It doesn't matter what base log you use. Equals ln of the height copy that down, and now if we graph the log of height by age, we see what we get. Chart, select data, add the series. We want x values to be the age and the y values to be the log of the height. And here we've squashed the axis, but we haven't fixed the linearity at all. It's still got a curve. It looks even more curved than the original data. So that we need one more step to do this. And this is a fairly common transformation for any kind of sigmoid curve with a growth type curve. And instead of age in years, we're going to use 1 over age, the reciprocal of age, equal to 1 divided by the age. So that we have the log of height now and the reciprocal of age. And if we graph the log of height as a function of the reciprocal of age, we get something that we can deal with. So we put a new scatter plot in. We'll put a new scatter plot in. And this time, the x variable is the reciprocal of age. And the natural log of height is the y variable. And when we do this and look at the graph, we get very nearly a straight line. so that I can put a straight line through here and it will fit very well. My assumptions are fulfilled. I have a straight line. I have no flare. If I look at the R-square, it is 0.974, so that I have a very good straight line relation, so that I can predict the height by taking the reciprocal of age times the slope, here it's minus 27.71, adding the intercept of 4.7, getting the predicted log of the height, and then taking e to the power of that log of height to get the original height back. This transformation has absolutely no justification mathematically or biologically. All it does is work, and that's all it has to do, so that we can make transforms on variables, both x and y, and all we have to remember is that we are no longer dealing with height and age directly. We are dealing with the log of height and the reciprocal of age, so we're minimizing the residual sum of squares of the log of height using 1 over age.